Okay, good afternoon. Well, I'm glad that there are still some people sitting in the room, because I heard of a lot of people that were going already for their plane or train or etc. But still some people that are interested. Thank you for that. So I will tell you something about a quantum algorithm that we made for technical capacity management in an electricity network, and that is common work with my colleagues Bart and Stan. We all work at TNO, and TNO is the Dutch Institute for Applied Sciences. So maybe a little bit of introduction to the problem. As you all know, there is a call for sustainability, and that means that we want to use new power sources more and more. Think of wind and sun energy, and also that we get other devices that are using electricity, like electronic cars. But the problem is, of course, that those energy sources are less reliable because of the fluctuation over time. And that means that it's sometimes, we want to use electricity, but there is no generation, and other times there is too much generation, and then we have to export it or store it. And the basic idea is that the demand and the supply of the energy are not matched very well. So what we can do to that is, of course, that we can transport those large amounts of energy to other places where they will use it, and that means that we have to do a lot of work on our energy networks, because they are not made for such big amounts. And especially in the Netherlands, we already see that they say the electricity network is full, so we don't have any capacity left there, and that will cause large losses in energy, because then we just have to switch off solar panels or the windmills in times that they actually could generate a lot of electricity. What we of course can do there is we can add more storage capacity in our network, batteries. We can use smart grids, so that we learn our equipment to use the electricity when it's there. But that takes time. And then the question is, why not start with the basic idea that we just have to match the supply and demand better? And there we come with the tactical capacity problem. The whole idea is that we want to match those two. So if we look at a neighborhood with some households, then, well, as a basic, they get their energy from outside their network, from a big energy generator. But in those days, those households are going to be prosumers, so they will both produce and consume electricity. And for those for that production, they have a probable generation profile that is stochastic, and they have some energy demand profile. And now the idea is, of course, that we have to match those two, such that a lot more of the energy that is generated is also used in those neighborhoods. And that's the main goal of this problem: find optimal allocations or assignments of the local energy generators for different power sources, such that the supply and the demand are matched better. For that, we can come up with a mathematical model that will minimize the total energy loss. And the idea there is that if the match is very well, so all the energy flow stays within one household, there's no loss at all. If we have to allow flows in the neighborhood, there is some small loss, and if we have to get energy from outside of the neighborhood, or we have to transport it outside of the neighborhood, then there will be big losses. And that means actually that the minimization of the energy loss equals the match of the supply and the demand. For that, to solve that problem, we use quantum annealing. Well, you've seen it before, I think, in this conference. So they solve the Ising model problems, and those Ising model problems are the same as the QUBO models, the quadratic unconstrained binary optimization problems that we saw before. And those are, those QUBOs can be solved, or not solved, but approximately solved by a quantum annealer. And we can model a lot of optimization problems in this QUBO formulation. The main idea is that we have to solve this formula where the x's are actually binary factors, and we have a Q matrix that have real value, that is a real value matrix, and we want to find the binary factor that minimizes this this function. And that means that we have to model our problem in that way. However, there is still some limitations in the hardware. So we have around 5,000 qubits, and that means that if we have to translate our variables to those qubits, we can have somewhere between 177 and 5,000 variables, depending on how the Q matrix looks like. So in a very dense Q matrix, we only have a very limited number of variables. And that means that if we want to bring that real-life problem into a QUBO, we have to limit the number of variables or the number of used qubits. So if we go a little bit more in depth into the mathematical formulation, then we look at a neighborhood with some houses, with some possible types of electricity generators and a certain time interval. And we want to decide which type of generator do we assign to a specific house. And then we have to think of that for every type of generator placed on a specific house, we have a specific production profile, and every house has its own consumption profile. And from that we can calculate the mismatch within a house. So that is the mismatch that when the production and the demand within a house in a specific time frame doesn't match. But also we have some mismatch in the neighborhood. So when the total production in a neighborhood and the total consumption on a specific time stamp doesn't match. And from that we can calculate the loss. So there we see that the loss factor, the p's here, are multiplied by the total energy flow squared, because the energy loss is a squared function of the flow. And that's also the reason why we came into this quantum annealing, or in quantum computing, because this kind of problems, which are quadratic from nature, are expected to be better solved on a quantum annealer than on classical solvers. So we used the quantum annealer to solve this, and that was already earlier by myself and a colleague. And what we saw that up to 1,500 houses, we were able to get results with a number of solvers. We had Gurobi that we already saw before today. We have local solver, another classical solver. We used stimulated annealing. We used the quantum annealer QPU itself, and we used the hybrid solver that is provided by D-Wave. And what we see here is that, so we solved the QUBO especially, and we know that Gurobi and local solver are good classical solvers, but not specifically for QUBO formulations. So we could have actually better given them the the constraint version of the problem, but we didn't. We gave them the QUBO, and we saw that, for example, that Gurobi was not able to solve problems bigger than 100 households. Local solver, simulated annealing were all able to solve all the problems. We see here the calculation times. Quantum annealing, so purely the one QPU chip, was also able to solve up to 100 households, and the hybrid solver could also solve all the instances here. Now you could say this is not an honest comparison, because we have really an optimal solver as local solver, and we have a heuristic approach that is the hybrid solver. However, actually, local solver was not able to really close the optimization gap. So what you see here in between brackets is how much of the optimization gap was he able to close. So how able was he to prove the optimal solution in 1200 seconds. And so the idea is that, for example, on the 250, you see 60 seconds. So after 60 seconds, local solver gave his best solution. But after 1200 seconds, the optimization gap was not closed for more than 55%. So it was still also a heuristic solution, you could say. But still, the hybrid solver is quite quick in solving this problem. And well, I don't know whether I said it already, but they all gave the right solution. So that was the first part. And then we said, okay, how can we improve this model? And the first step is to add constraints here. And the most obvious constraint is to introduce capacity constraints to the cabling, because if you don't do that, then your cables will look like this. So they will melt in some way. So we want to introduce the constraints here. But the problem is, if you add constraints, more constraints, and especially inequality constraints, they will come with a extra number of slack variables. And the more variables, the more slack variables you introduce, the worse the solution will be that the quantum annealer will give us. So then the idea is, okay, how can we, in one hand, add more constraints, and in the other hand, reduce the number of variables that we use here. And we use two ways of reducing those variables. The first one was that we looked very carefully at the constraints that we added, and we said, okay, some constraints we do not need to add. For example, a capacity constraint on electricity flowing outside of the neighborhood at night is not necessary, because there will be no sun, for example, so you will not meet those capacity constraints. Another one is a more technical way of removing auxiliary variables, and that is by using the approximation constraint. And there the idea is that if you have an inequality constraint, so like the summation over ax smaller or equal to b, well, that costs a lot of auxiliary variables to implement this formulation. And we could also replace that by dividing both sides of the equation by a value rho, and that would decrease the number of auxiliary variables by the log of rho. But that comes with a cost, because it's an approximation. So we have to look at how the reduction of the number of variables counts with respect to the solution quality. Was it 2 steps? No. Okay. So that gives us the final QUBO formulation. The first 3 lines were already introduced before, and now we get 2 more capacity constraints, where all the yellow parts actually are the parts that we try to reduce the number of auxiliary variables. So to test this, we used a dataset with both a supply and a demand profile. So for each household, we generated a variable demand around a base pattern. And for each house, we generated a orientation, and the orientation says something about the supply of the solar panel during time. So we did that for up to the 1,500 of households. And then we did the analysis in 3 different cases. So the first case is that we use all the constraints. The second one is that we introduce the removal of the unnecessary constraints. And the third one, that we add the reduction with the with rho is 10. So we divide both sides of the capacity constraints by 10. If we look at the numerical results and then we look at the QBO size based and the ratio of the auxiliary variables given the number of households that we have in the problem, with no reduction, we see this function. And then if we introduce the first way of reducing it, we see that indeed the fraction of auxiliary variables goes down a lot, actually. And adding the second way of reduction, so the approximate constraints, gives a small extra decrease in the fraction of auxiliary variables in the problem. So that works. And to see something about the quality effects, we looked at 2 backends, both the quantum annealer, so the D-wave annealer, and simulated annealing, and we looked whether they have a different behavior on these reduction steps. And if we look at the solution quality in quantum annealing, this is then the case with no reduction, and so we are only limited to a very small problem size, to 10 households. If we introduce the removal of the unnecessary constraints, we were able to solve up to 100 households, and we see that the quality is a little bit worse, but not much. And if we then introduce the approximate constraints, there we see that it gives a worse solution in the beginning, but almost the same in the rest of the trajectory. In computer time, it does more, so it really decreases the computation time on the quantum annealer if we get a reduction. But what we see is in the end, they are going to start to be the same, approximately there. In simulated annealing, so then we can go to higher numbers and maybe say something about how it will work for bigger problems. So there again, with no reduction, with the removal of the unnecessary constraints. So we see here actually almost no effect in the objective, and again almost no extra reduction in quality with the second step. And in time, also here we see a reduction in the computation time, however not as much as we saw on the quantum annealer, because there a lot of the computing time is taken up by the embedding of the problem. So, as a conclusion, the basic idea is if we want to meet the sustainability goals, we also have to think about a better matching of supply and demand on a more technical level. as being a quadratic problem by nature, it could be a promising application. We were able to solve some real-life problems here on the quantum annealer or with the hybrid solution that D-Waves provides, and we were able to get some improvements to the basic models by adding more constraints, and still we could lower the number of the variables that were added here. Yes. Any questions?
Yes.
Yes, actually I have thank you for this presentation. I have two very quick questions. I didn't get really the thing for the solution. You know, you have this table in which you show between brackets the percentage of what is the gap to the optimal solution.
Yeah.
So this is my first question. The second question is how you can qualify that you are converging to an optimal solution. Do you have a reference of what the optimal solution look like, or?
Yes. So the first one is that in solving mixed integer problems in a classical way, what you actually do is you try to find a integer problem, and you solve a relaxation of that problem. And the idea is that at some place they are meeting each other. Then you know that the integer problem that you found, that it actually is the best integer problem, the best integer, so it's the solution. And that process is called closing the optimization gap. So as long as that's not closed, you're not sure that you have the optimal value. So, with this problem sizes, we could actually let him run all the time until he closes the optimality gap. So we were, in the end, sure that it was the optimal solution. If you get bigger problems, of course, then that will not be possible.